Hi everybody, welcome to Autodesk Simulation TV, Simulation in Action. Today we're going to be talking about Autodesk Simulation Moldflow and in particular Core Shift. My name's Matt Jaworski and I'm a technical specialist here at Autodesk. Core Shift is a particular problem that happens with molds, and what we're going to do is look at an exercise today of how we can simulate core shift on a medical syringe part. Some of the key learning objectives we're going to have today are creating and importing cores, the requirements of a core shift analysis, how to do it, how to set it up, and how to review the results after the analysis is complete. What exactly are we looking for here, and what problems are we going to anticipate that are going to happen in production? So before we get started, let's take a look at what is core shift. So core shift is a spatial deviation from the original position of a mold core. So as the plastic comes in, it builds up pressure on the inside of the mold, the core. The distribution is going to cause the core to shift. And that pin is going to shift and cause different thicknesses in the part from one section of the part to another, which is not what we designed for. So we want to be able to anticipate this before we build a mold, and hopefully build a core that's strong enough or maybe change materials so that this does not happen. So why would we run a core shift analysis? As we go through the injection molding cycle, the core is going to shift, and the moving core is going to have manufacturing ramifications to our product. There may be changes in the wall thickness. The filling pattern may change because of those changes in thicknesses. The plastic is going to go where there's least resistance. It can introduce weld lines or air trap issues in the model where we don't want them. And because the core is flexing and then releasing, flexing and then releasing, we may get fatigue or even premature part failures in the part. So when should we run a core shift analysis? Well, typically we'll run one when there's a long unsupported core or a cantilevered type of system. If the core is constructed out of a low modulus material, that means it's flexible. That's also a reason why we'd want to run it. If we have small part inserts that are thin, that could move, or maybe we have sheet metal inserts that we want to mold around, those are also good reasons. If we are in a two-shot molding process, we may want to run core shift on the first part to see if it affects the second shot. And also we want to run a core shift analysis to determine if those moving cores are going to influence warpage. So the first thing we want to take a look at is building a core. Now, in previous simulation TV videos, you've seen how to create a mesh and bring a part in and go through that pre-processing of the model. What we're going to do here is break and go into showing you how to model a core, because that's something that's different from the previous videos. First, we're going to import a core that was created in a CAD system, in this case Inventor. And what we're going to do is bring the model in and show you some of the options that we can have to bring that core in and how to set the properties. So let's go ahead and get started. So here we are in the Moldflow software, and one of the first things that we need to do is import a product. So I'm going to create a new project and just give it a name. We'll call it Core Shift. And then we'll go ahead and do the importing process. So when we import, we have to look for a model that contains an assembly. Now in this case, we're going to use the syringe with core IAM assembly. When we import, we have a couple different options. So Autodesk Simulation Moldflow Design Link is a tool that you can use to import not only native Inventor files from Autodesk, but also several different CAD systems. So when we import the model, we're going to choose a mesh type as 3D. And we can choose to use the Moldflow Design Link to process the model coming in, or we can just read it in as the CAD system, those solids, and then mesh them when they're in the program. So just to show you the differences, the first one we're going to do is within the Moldflow Design Link software. So there is, once you check it off, an advanced option that you can use. When you go into the advanced option, we can generate the mesh, we can define edge lengths. I'm just going to make something that's relative. So I'm going to use a 0.1 inch mesh for our global edge length. And I'm also going to turn on chord height. And what this will do is make it so that our cylindrical surfaces have more facets, or it's essentially more detail to give that concentricity of the model more facets or more mesh. And probably the most important option on this screen is to have both the core and the cavity that we're going to read in as an assembly be precisely matched. Because if we have something that's a different mesh on one side compared to the other, we may not have enough tolerance in the system so that the pressure on the cavity transfers over to the core. So it's important that we have a good tolerance or matching between the core and cavity so that when the core shift analysis occurs, they'll be able to transfer the results back and forth. So after we've chose all of those different options, we can just go ahead and hit OK and let the software read in the model and mesh it as part of that process itself. So now we see the model inside of the software. And when it read the model in, it actually meshed it. So we have two separate mesh layers, one for the cavity, and if I turn that off, one for the core. Once we bring the models in, we can then set up the properties that we would for a normal filling simulation or filling and packing simulation inside of Moldflow Insight. The only difference is now that we have a core inside of there that we want to run a core shift simulation on. So we do have to set up some properties to that. In addition to the first option, which was the easiest, we can also create a core from the part mesh inside of Synergy. The benefits of doing this is that you can create an exact duplicate of the inside of the model, which is forming the core. So how we would do this is we would run and import the model, we'd create a dual domain mesh, and then we'd delete the elements that weren't touching the core. So essentially creating a copy of the part that we have and then using it as a building block for the core. So what would happen here is we delete those elements and then we'd fill in any of the holes that were in the solid that weren't touching, for instance, the top of the core or maybe some of the sides. And then once we created a full 3D solid, we convert that over from a dual domain mesh to a 3D mesh. Then we'd set the property to a core 3D or a part insert 3D. The difference being is a part insert 3D allows us to set an instantaneous or initial temperature so that we can have the core at a different temperature than what the mold temperature is. And then we'd add that core that we created back into the part study to run the core shift simulation. Another tool that we can use is the Geometry Create Insert tool. This allows us to create a copy of the dual domain part mesh and then use that part mesh that's touching the core to create a new part or an insert. In this case, we're going to place all the elements that are touching the core onto a new layer. So you can create a new layer, select them with normal selection techniques, and then put them into that new layer. Then what we're going to do is cap off that layer if there are any holes. So we can use the Fill Hole tool, for instance, to create a surface that is continuous. Then what we're going to do is use the Create Inserts tool to select that newly created layer of elements and build the insert from that in typically the negative Z direction. Then we're going to delete all the elements that are not part of any of the other insert, clean up the mesh, and then convert that solid insert that we created into 3D mesh. Finally, we'll set the properties of the core insert itself, either core or part insert, and then we'll add that back to the part study. Now we have to create some properties on the core to tell the software that this is the core insert itself. So the easiest way to do this is to just box in the core with nothing else visible in terms of the layers. So we have our core layer visible. We're just going to go ahead and left click, hold it down, and select all of the core elements that we're going to convert. Then we can right click and change the property type to either a core 3D or a mold insert. In this case, I'm going to use core 3D because I don't want to have any other initial temperatures other than the mold temperature. And then what I'm going to do is go in and right click again and look at the property itself. As part of the properties, we can set this up to be a metal or a plastic insert and use any of the standard material database files that are inside of the program itself, or create a new one on our own. I'm going to go ahead and select a metal insert, and we're going to use a standard P20 insert to start off with. Now again, we can go in and select any one of hundreds of different types of materials if that's not the one that you want to use, or create our own. So I'm going to go ahead and use that particular P20 material for our core insert and hit OK. The other thing that we have to do is now we have a material defined for our insert, and now we have to tell it how it's constrained. So let's go back to the PowerPoint and see how that option occurs. Core constraints are something that we need to define in order for the insert of the core to be constrained during the analysis. The reason why we have to do this is it prevents rigid body motion in the structural analysis, so that when the polymer hits the core, it can take the loads that are on it. What we will do is we'll go into the constraints of this software, and we'll set up fixed constraints at the bottom section of the insert. And this will provide everything that we need for the pressures to develop and how it's going to actually be constrained in the mold. So here we are back inside of the Moldflow Insight software, and we have to set up that constraint that we just talked about. So in order to do that, we have the mesh visible, but not the nodes. So if we go down into the layers panel and click on nodes, now they'll be visible for us to select. And to put constraints on a model, we just simply go up to constraints, and then the constraints that we want to use are fixed constraints, so we'll select that. And because this is a core shift analysis and not specifically a stress analysis, we will use this pull-down menu to just use the core shift analysis constraints. And finally, what we need to do is select the nodes. So the easiest way to do this, in this particular case, is we're going to constrain the bottom edge or surface. So I'm going to select just inside of that bottom edge, hold down my left mouse button, and select the bottom of that particular core. And as I rotate it around, you'll see that all of these nodes are selected and put into the selection box. And then all we have to do is apply them. And it creates a new layer on the bottom called Fixed Nodal Constraints, and also makes them visible on the screen for us. Now what we have to do is set up the analysis to know that it's running a core shift analysis. So everything up to this point is going to be very similar to setting up a filling and packing analysis in a regular type of fashion. So I'm just going to right click and set the analysis sequence so that it includes filling and packing. And then I'm going to go under the process settings and make sure that under the advanced options, solver parameters, click edit, and we have a tab in here that's called core shift. We want to make sure that the perform core shift analysis is turned on, which it is, and then we can adjust some of the settings that are in there. So for instance, if we don't want every 5%, maybe that's too much, or too little. Maybe we'll go down to 2%. And every 1/10 of a second, that should be perfect. So you can adjust this so that you get more or less results over the sequence of the analysis. And what's going to happen is it's going to run the filling analysis, stop, apply the pressures to the core, run a structural analysis, an FEA analysis, shift the core based on those pressures, and then keep doing that process. And as it does that, it adjusts the thickness of the model itself on the part. So as the core shift, the shift that happens, the thickness will change on one side of the part compared to the other. And we can also have it do that rather than just the filling phase, check this box off, and then have it also do it in the packing phase. We also have some other options that we can go through. We can fix core temperatures or assign a temperature, but for all intents and purposes here, we'll just go ahead and leave those defaults. Then hit OK, OK, and then finally OK again. Now that we have the core shift analysis set up, I want to go back and bring up the part, because one thing that we can't do is run yet. And the reason why is because we don't have any injection locations on this part indicated by this icon here. So what we want to do is essentially zoom in on a section of the part and apply an injection location, or we could build a runner system on this in multi-cavities if we wanted to. To keep it simple, we'll just put one injection location on. So I'm going to click on injection location and then place an injection location somewhere on the part so that we have an area for the polymer melt to come in. So now we're all set up to run the analysis, so I'll go ahead and start it. Now the analysis is started and running. Now the analysis is complete. So what we want to do is take a look at the results that are generated by this analysis for core shift. The first thing I'm going to do is turn off the logs so that we get a graphic screen back. And then I'm going to go ahead and look at some results. So for instance, fill time. I'll turn that on, go under the results section, and then animate the fill time pattern to see if there's any shifts in the fill pattern from one side to the other. It looked pretty even except for the beginning. So I'm going to just back it up to take a look at that. So as we inject on one side of the part, we can look in or zoom up and see that half of this core, or this side of the core, is seeing pressure, whereas this side is not. So that's probably going to cause the shift in the core itself and change the thickness on the top. So we'll investigate that a little further. But let's take a look at the results for core shift analysis. So under the bottom of the screen, we have displacement's core. And what displacement's core shows us is the core itself over time shifting. So if we go ahead and animate this, we can see how that core is shifting over time in the cavity itself as it goes through filling, packing, and cooling. And if we look at it from a top view, we'll be able to see that movement, in this case of about almost 17 thousandths of an inch. So if I zoom up so I can see from a top view and animate the model, we'll see it starts off very nice and centered, and then as we build up pressures on one side of the core, it shifts over so that we get a thinner area at the top and a thicker area on the other side. So let's take a look at what that actually did in a final displacement. And I'll turn off the part cavity so that we can see just the core itself. So I'm going to turn off the part and look at the core. And what we see here is this is the final shift that's happened after the part is solidified. So it's different or moved about 17 thousandths to the left-hand side of the screen. And finally, we can take a look at stresses that are on that core itself. So as I look at the core, I'm going to go ahead and click on the isometric view. So we can see on both sides we do have some stress on the model. We can go up and examine those results to see what the stresses are, or simply match it up to the color scheme that's on the side of the screen. Now I like to see the plot update over time. So what I'm going to do is go under the plot properties and go under scaling and make it per frame so that the highest and lowest values of the model or results are displayed over time. And now when we go through and we animate, what we see is we have some initial pressure built up, then the core is shifting and building up pressure from one side to the other. So we can see those values change. I'll go ahead and animate it again because it was a little quick. We see the pressures build up, how high they get, and as they go through filling and packing, how that pressure changes over time. So that's useful information for us if we see a fatigue where the core is bending, coming back, bending, coming back. Over time, that may fatigue the core and give us cracks or breaking, and particularly if we have cooling going up the inside of the core, it thins the wall, so we may see water leaks, or we may see that the core is permanently bent as we go and we fill the part, and we can't figure out why from processing that happened. The software will allow us to take a look at these results and draw some great conclusions of why core shift is happening. Can we prevent it? Can we change materials? So what I can do is after I get these results, I see what the core shift is, and maybe I want to try a more flexible material. Maybe the P20 wasn't extracting enough heat out of the model inside of the core. Maybe I want to go to like a high thermal conductivity material like a beryllium copper. So what I did is I ran another analysis that changed the properties of the steel. So just very quickly, in order to do that, I would just go in and make a duplicate by right-clicking on the study file that I'm currently working in and going down to duplicate. It says, do you want to save those? I definitely want to save all of the model changes and results that I've done up to this point. And then I'm going to give it a new name. I'm just going to go ahead and accept the default. And then I can double click on it to open that particular model. So I've created a copy of everything I've done before, so the results come with it because nothing has changed. So now I can change the property of the core. So what I'll do is select the entire core. I will right click and go under Properties, and I can select a different material. So remember we used P20 before. What I want to go into is the Select button. And then I can use things like beryllium copper, brass. There's a whole list of hundreds of different types of materials inside of here. I'm going to choose a common beryllium copper material, which is a mold max, in order to see what the differences would be in core shift between that material and another. So we could select that material and then go ahead and run the analysis again and see the results. So this can be a very iterative process where we take a look at multiple core materials, different configurations. Do we have cooling inside of the core, or is it solid? And really gain some useful information before we build a tool and have problems. And that's really the name of the game in simulation. I'd like to thank everybody for listening to today's presentation on core shift. I encourage you to go to SimTV and look for other videos. I'm Matt Jaworski, and thanks.